Okay, in guide sheet number 2 for conservation laws, we're going to look at the concept of power. Uh, Power is a rate quantity. Power is defined simply as the rate at which work is done. So rate of doing work. And rate means time, means essentially to divide by the time that it takes. Quick review of work. A force acting upon an object causes displacement. Moving something by applying a force is known as work. Two acceptable units for work are force times distance, that's Newton meter. 1 joule is defined as the amount of work done when you apply a force of 1 Newton through a distance of 1 meter. Now, power is a rate quantity, so therefore power is defined as the rate at which work is done. Okay. If two machines do identical jobs, do the same work, yet they have different power inputs, how could that possibly be so? Well, again, power is not just work, it's work divided by time. So if one machine does the work in less time, even though they change the same amount of energy, the one that does it in less time has more power. Okay, in terms of units, back in the early 1800s, James Watt was busy trying to improve the steam engine so the Industrial Revolution could take off. In doing that, he did some experiments with horses, and so we've gotten a unit. The unit of power in the system, international system, is called the watt, and 1 watt. And you have to be careful here because watt's a capital W and work is a W, often a capital W. So be careful. Don't confuse those two. They're not the same. Is equal to 1 joule of energy changed per every 1 second of time. So power is work divided by time, so joule per second would be an acceptable unit. The watt is the name for that derived unit. Now, Watt worked with horses, and the first thing he came up with was the idea of horsepower. He needed to be able to show the mine owners that his machine could work more than their horses could. So horsepower is still a unit we use today. We talk about, especially with cars, lawnmowers, and so forth here in the United States. In most of the world, they use the kilowatt, or thousands of watts, not the horsepower. Okay, number 6, we have 2 students lifting the same amount of weight, the same amount of time. Essentially, they're doing the same amount of work. So neither does more work. They're both overcoming the same weight. They're overcoming it the same number of times. If we assume that their stretch or arm length is the same, they're doing the same amount of work. On the other hand, though, Ben does that work in only 10 seconds, whereas Will takes a full minute to do the work. So that's going to make Ben more powerful because Ben does the same amount of work, but in less time. And again, power is a rate quantity, so it's really not about per se the work you're doing, but the time that it takes you to get it done. So it's a combination of both. So while they both do the same amount of work, Ben does it in less time. One of the ways you can measure your power is to run up a set of stairs or a hill. In this case, we have Jack and Joe running up the hill. Jack has twice as much mass, so he will do twice as much work because he's going to have to move twice as much weight up the hill as Jill does. But Jill does that half as much weight, so she does half as much work, assuming they move to the same height, but she also does it in half as much time. Okay. So by doing the same less work but doing it in less time, Jack does more work but neither deliver more power. They both end up with the same power rating, the same number of watts. being used. Again, that's their number of joules, or their conversion of energy per second. So it tells us how fast they're using the energy, not the total amount of energy used. Now, when we think about power, often we think about like races, with the person who gets to the finish line first, least amount of time, is going to be more powerful. We can bring in velocity with power. If you look at the idea of power, it's work over time, and work is a force times a distance, a change of position over time. Well, if you take delta S, change of your position over change in time, that's the rate of change of position, which is the same as your velocity. So another way to calculate the power of an object or objects is to determine how much force is being used to move it and how fast is it going. Okay, so we'll apply those equations of power in the next episode of this guide sheet and practice calculating power in watts and work in joules.